Lesson: Understanding Convolutional Neural Networks, CNNs. Understanding convolutional neural networks is central to mastering computer vision theories, especially within the context of a certified AI implementation professional course. CNNs have revolutionized the way machines interpret visual data, making them indispensable for professionals seeking to leverage AI in practical applications. These networks excel in tasks involving image classification, object detection, and facial recognition, owing to their unique architecture and ability to automatically learn spatial hierarchies. This lesson delves into the core principles of CNNs, offering actionable insights and practical tools to enhance proficiency in this field. At the heart of CNNs lies their ability to process data with a grid-like topology, making them particularly well-suited for image data. Traditional neural networks falter with image data because they do not scale well with high-dimensional inputs. In contrast, CNNs efficiently handle the spatial structure of images through layers that perform convolution operations, a mathematical operation that combines two sets of information. The convolution operation in CNNs involves a filter or kernel sliding over the input image to produce feature maps. This process enables the network to detect various features such as edges, textures, and patterns, which are crucial for image interpretation. One of the practical tools for implementing CNNs is TensorFlow, an open-source machine learning framework. TensorFlow provides a high-level API known as Keras, which simplifies the construction of neural networks. With Keras, professionals can easily define and train CNN models. For instance, building a CNN for image classification involves specifying layers such as conv2D, max pooling 2D, and dense, which are integral to CNN architecture. The conv2D layer applies convolutional filters to the input, while max pooling 2D reduces the spatial dimensions, crucial for managing computational complexity and preventing overfitting. Finally, the dense layer connects the high-level reasoning to the output layer, which predicts the class probabilities. In practical applications, CNNs have been instrumental in advancing fields like healthcare, where they assist in diagnosing diseases from medical images. A notable case study is the application of CNNs in detecting diabetic retinopathy from retinal images. Researchers employed CNNs to classify images into different severity levels of the disease, achieving performance comparable to human ophthalmologists. This success underscores the potential of CNNs to augment human expertise, reduce diagnostic errors, and improve patient outcomes. Moreover, CNNs address the challenge of feature selection, which is a significant bottleneck in traditional image processing methods. Unlike handcrafted features, CNNs automatically learn hierarchical features from the data. The initial layers detect low-level features, like edges, while deeper layers capture more abstract features, such as shapes and textures. This automatic feature extraction capability reduces the reliance on domain expertise, enabling CNNs to generalize well across different datasets and tasks. Another critical aspect of CNNs is their ability to leverage transfer learning, a technique that enhances model performance by utilizing pre-trained networks. Transfer learning is particularly beneficial when labeled data is scarce, a common scenario in real-world applications. By fine-tuning models like VGGNet, ResNet, or Inception, professionals can achieve high accuracy with minimal training data. Transfer learning not only saves time and computational resources, but also improves the robustness of the models, making them suitable for deployment in diverse environments. Despite their numerous advantages, CNNs also present challenges that professionals must navigate. One such challenge is overfitting, where the model performs well on training data but poorly on unseen data. Overfitting can be mitigated by techniques such as dropout, which randomly disables neurons during training to prevent the network from becoming overly reliant on specific paths. Additionally, data augmentation, which involves artificially enlarging the training dataset through transformations like rotation, flipping, and scaling, helps improve the model's generalization ability. In the realm of computer vision, CNNs have set the benchmark for performance, but understanding their limitations is equally important. CNNs require substantial computational power and memory, which can be a barrier for deployment in resource-constrained environments. However, advancements in hardware, such as graphics processing units and tensor processing units, have alleviated some of these constraints, enabling real-time processing and deployment of CNN models even on mobile devices. Furthermore, the interpretability of CNNs is an ongoing research area. While CNNs demonstrate remarkable accuracy, their decision-making process is often opaque, posing challenges in applications where transparency is critical. Efforts to demystify CNNs include visualization techniques like class activation maps, which highlight the regions of an image that influence the model's predictions. These techniques not only enhance trust in AI systems, but also provide insights for model improvement and debugging. CNNs continue to evolve, with architectures becoming more complex and specialized. Recent innovations, such as attention mechanisms and capsule networks, aim to address some of the limitations of traditional CNNs. Attention mechanisms, for instance, allow models to focus on relevant parts of an image, improving performance in tasks like image captioning and object detection. Capsule networks, on the other hand, strive to capture spatial hierarchies more effectively, promising improvements in scenarios where viewpoint variations are significant. In conclusion, understanding CNNs is crucial for professionals navigating the landscape of computer vision. By leveraging frameworks like TensorFlow and techniques such as transfer learning and data augmentation, practitioners can build robust models that address real-world challenges. While CNNs offer remarkable capabilities, being cognizant of their limitations and staying abreast of emerging trends will empower professionals to harness their full potential. As CNN research progresses, the fusion of innovation and practical application will continue to drive advancements in AI, opening new frontiers in how machines perceive and interact with the world.